Hello backbenchers, how you all are doing? I hope you all are doing really great. So in previous video we have started our new subject, which is fluid mechanics, and in the first part of that fluid mechanics we started the basics of fluid mechanics, what is fluid, how it reacts, and what are the properties of fluid. So if you haven't watched the video, please go and watch the video in the playlist of the fluid mechanics. Now today we are again going to start the part 2 of basics of fluid mechanics, in which a few of fluid properties are left, and yeah, some type of fluid we are going to talk about. So yeah, let's get started with the first remain property of the fluid, which is the surface tension. So let's go. And one more thing guys, please watch the full video, and if you like the video, please give it a thumbs up, and if you are new to our channel, don't forget to subscribe and hit the bell icon for more further videos on the channel. So now let's continue with the surface tension. So what is the surface tension? So surface tension is the tensile force acting on the surface of a liquid in contact with the gas, or on the surface between two invisible liquids, such that contact surface behaves like a membrane under tension. What it is saying, so let's just keep it aside this definition, because it is quite confusing. Now let's understand the concept, what it is trying to say. Okay, so let's take a container and fill it with some kind of fluid here. Okay, now let's take three fluid particles over here. One is at the bottom of the particle, which is bottom of the container, which is A. Second is at the mid part of the container, which is B, and the third one is at the top layer of the fluid, which is, we name it as C. Okay, now what? So if the particle is at the bottom, then the pressure will generate due to this fluid. Okay, so due to this fluid, the pressure will generate on this particle. Then the some kind of tensile force, which we can say is the tension force, will occur on the surface of this body of, or this particle in the container by the fluid. Okay, if is it clear, then it is okay. Now let's get on the another B point. Okay, so now this time it will, I hope it will be clear. So now let's say that it is at the mid. Now again the tension or the pressure will generate on this B part, and again by that pressure, the tensile force will occur on the surface of the body or the particle here. Okay, by this tension force will generate on the surface of the body, and this generated surface tension is called as the surface tension. Now let's take the third C point, C particle, where it is half is below the water, or sorry, half is below the fluid and half is above the fluid. So on this, which is above the fluid, there is not any pressure is occurring on the above surface of the particle here. So this part, there will be no pressure will occur. So now what will happen? This part will remain nothing. Okay, now all the pressure will generate only here only. Okay, and by this pressure the tension will also occur. So now this time the surface tension will occur on this section only. On this section the surface tension will only occur on this section only. And we can say, with in contact with gases, the surface tension can also occur on the layer, on the top layer of the fluid also. So this is the total concept about the surface tension. The magnitude of this surface tension is per unit per meter, which is the unit of the surface tension in MKS. We can say it is kgf per meter, but in SI unit it is Newton per meter. The surface tension is measured in these unit. In MKS it is kgf per meter, but in SI unit it is measured in Newton meter. Now if we talk about the conditions, the cases of the surface tension, there are three cases will occur in the surface tension. First one is the hollow bubble tube, and the second one is the jet case, and the third one is water droplet. So let's get to the points, the cases of we have here surface tension. And one more thing, surface tension is represented by the sigma. Okay guys, so let's get. Okay, so the case one is for the surface tension on the liquid droplet. So for the liquid droplet, let's consider a spherical liquid droplet. Now let's cut it into two parts. Now let's consider this part only. Okay, so now if we consider this part, this will look like this in 3D image. This will look like this. Now now what will happen? For the surface tension on the it will shows on the surface like this. Okay, now if we talk about the pressure, how will the pressure acts on this by this surface tension? So it will act like this. Okay, so it will act like in the droplet. This is pressure force and this is the surface tension which is sigma. So that is pressure and this is sigma. So here we have the droplet. Okay, and what is this? This is the surface tension and this is the pressure condition here we have. Now if we calculate about the surface tension here, then we know that the sigma is equals to, which is surface tension, and also we call it the stress, is pressure upon load upon area or the pressure upon area. Now if we talk about the surface tension, then we can calculate the tensile force, because what is surface tension? Surface tension is the tensile force acting on the surface of a particle. So let's say that the tensile force, which is Ft, we can say what will be the we can also write it as F also. Okay, so F is equals to sigma into A. So on if there is it is acting on the circumference, so what will be the area? The circle circumference, or obviously the circumference will count us. Okay, so the circumference of the circle is pi d into what we have here, sigma. So it is Ft is equals to sigma pi d, which is equation 1. Now let's talk about the pressure situation. What is going to happen in the pressure situation? The pressure situation will be like this. Fp is equals to, here it is acting on the whole area of the droplet. Now what will gonna happen? The area will be pi by 4 d square into the pressure which is acting, the load which is acting here is pressure. So pi by 4 pi by 4 d square into p, which is equation number 2. Okay guys, so now let's equal the equation 1 and equation 2. Equation 1 is equals to equation 2. What will we get from this? Pi d sigma is equals to pi by 4 d square into p. So what we have here, we will get from this equation that P is equals to 4 sigma upon D. How we will get it? D is cancelled, the D square, and the sigma will the 4 is went here and the pi cancelled by this pi. So now we have P is equals to 4 sigma upon D for the liquid droplet. It is the surface tension for the liquid droplet. Now let's move on to the second case, which is for hollow bubble. So in the second case, the surface tension on hollow bubble will be, the calculation will be the same, but the value of this time will change a bit. So what will be the value? So P is equals to 8 sigma upon D will be the value of the second case on hollow bubble. If we talk about the third case, which is on the liquid jet. Okay, so what will be on the liquid jet? We have the pressure value here. So it will be like P is equals to 2 sigma upon D. Okay, in liquid jet it is a cylindrical shape. It is a cylindrical shape like this, and if we cut out it, then it will be like this. And on this surface we will find out the surface tension, and the total pressure will act like this, and by the calculation like the first case we will get the value P is equals to 2 sigma upon D. For the hollow bubble we will get the P is equals to 8 sigma upon D. Now if we talk about what will be the relation in between all of you, just to remember the values, because it will be quite confusing, because if we remember it is easy, it seems really very easy, but in exam we forget the values of these. Okay, so just to remember the thing, let's take first the hollow bubble. Okay, the hollow bubble ratio. The second one is the liquid droplet. Okay, liquid droplet. And the third one is the liquid jet. So just to keep it remind that what it is. Hollow bubble is 8 sigma upon D, and what is droplet is 4 sigma. The liquid droplet is 4 sigma upon D, and what is liquid jet is 2 sigma upon D. If we take out the ratio, then it will be like 4:2:1. Just remind, keep it in mind, 4:2:1. That's it. Then now next time you are not going to forget this thing. Okay, so now let's get on to the next property of the in the fluid mechanics, which is capillarity force, the capillarity rise and the capillarity fall. So now let's understand what is capillarity. Okay, so capillarity is the rise of liquid when the small dia tube is immersed in the liquid. This is known as the capillarity. So if we talk about, there will be two conditions for the capillarity. One is capillarity rise and the second is capillarity fall. In the capillarity rise, the liquid will rise in the tube when it will be immersed in the liquid. Now the capillarity fall, the fall of liquid will be in the tube when the tube will be immersed in the liquid. Okay, so now we talk about one more condition when the capillarity rise will happen, when the adhesive forces are the greater than the cohesive forces. When the adhesive forces will be greater than the cohesive forces in the liquid, then the capillarity rise condition will occur. Now if we talk about the capillarity fall, now if the cohesive forces are greater than the adhesive forces, then the capillarity fall condition will occur here. So these were the two conditions of the capillarity. Now we will find out the equation for the capillarity rise and capillarity fall. So let's see. So the equation for capillarity rise or capillarity fall will be like this. Now let's take a container again. Now fill it with liquid. Now we will immerse the small dia tube here in the fluid present here. Now the diameter of the tube will be D, and when we immersed in the fluid here, now the rise will occur or the fall will occur. We will name it as H. The height of the rise or fall will be H here, and the angle which is occurring between the tube and the rise of the fluid, the layer between it is called as angle of contact here. Okay, so now let's start the condition. Okay, so first will be, now we will find the weight of liquid present in the tube. So for this we will take out this volume of here. So what will be the volume? Area into height, now into density into gravity, rho g. Okay, so what will be the area of this? Pi by 4 d square into what will be the height? Height is the h into rho g. So what will be the equation here? Pi by 4 d square rho g h. We will name it as equation 1. Now the second equation will be here is, for the second equation we will find out the vertical component of the surface tensile force. The vertical component of surface tensile force. So for this, what we will do here, it will act on the surface. So on the surface, it is sigma into circumference into cos theta we will use here. So for the sigma, what is the circumference? Sigma pi d sigma cos theta. So this is the equation number 2. So we have here the equation number 1 and the equation number 2. Now we will equate the equation number 1 and equation number 2. So putting the equation number 1 and equation number 2 here, we will find out the height equals to 4 sigma upon rho, 4 sigma cos theta upon rho g d. Okay guys, so if we put this is the equation of the capillarity rise or capillarity fall. Now if we take the theta is equals to 0 degree, theta is equals to 0 degree. Now what will be the equation here? H is equals to 4 sigma upon rho g d. Now one more thing here, if theta is equals to 0, we take it theta is equals to 0 for the water, and for mercury, which is Hg, for mercury we take the theta here is equals to 128 degree. Okay guys, so this is all about the capillarity rise and fall. We have talked about everything. Now we will move on to the type of fluids we have in the fluid mechanics. Okay, so types of fluid here we have here four different types of fluid. One is ideal fluid, second is Newtonian fluid, and third is non-Newtonian fluid, and the final is ideal plastic fluid. So now we will understand the conditions of these fluids. Here I draw a graph here. I plot the graph is called as rheology. Here we have the shear force increasing on the upward direction, and the velocity gradient, which is du upon df dy. We have already studied about this in the viscosity in the previous video. If you haven't watched it, please watch that video. Okay, so now if we talk about the ideal fluid, so ideal fluid is the fluid which do not have the viscosity and which is uncompressible. Okay, uncompressible. So the fluid which has no viscosity and which is uncompressible, the fluid is called the ideal fluid here. Okay, now we talk about, there is no such kind of ideal fluid, and if there is any fluid which is real, then the fluid will have the viscosity and can be compressed or non-compressed, but the fluid will definitely going to have the viscosity. That's what it is called, the real fluid. So what is the real fluid? So the real fluid is the fluid which is having the viscosity is called the real fluid. Now next jump to the Newtonian fluid. What is Newtonian fluid? Newtonian fluid are the fluid which obeys the Newton's law of viscosity. What is Newton's law of viscosity? What is the Newton's law of viscosity? Newton's law of viscosity is the shear stress. The shear stress is proportional to the shear strain, or we can say the velocity gradient. Shear strain, or we can say the velocity gradient. Okay, that's why the line of the Newtonian fluid is the straight in this graph. It will increase as the shear force increase, then it is proportional to the shear strain, then the velocity gradient or shear strain will increase also. That's how it will work, the Newtonian fluid. The examples of Newtonian fluids are all the fluids like kerosene, diesel, water, mercury, and other fluids are the examples of the Newtonian fluid. Now if we talk about the non-Newtonian fluid, so the non-Newtonian fluids are the type of fluid which do not obey the law of Newtonian fluid. Look, these both are the real fluids. Okay, they both have the viscosity, but these Newtonian fluid obey the Hooke's law, but the non-Newtonian fluid doesn't obey the Hooke's law, in which means the shear force is not proportional to the velocity gradient, or we can say the shear strain here. The examples we can say is the toothpaste or the human blood is the example. Toothpaste and human blood are the example of non-Newtonian fluid here. Okay. Now if we talk about the last fluid here, so in the ideal plastic fluid, the value of shear stress is more than the yield value. And in the ideal plastic fluid, shear force is also proportional to the velocity gradient, or we can say it is the shear strain. Okay, so the example of ideal plastic fluid is the cold cream and toothpaste, we can say. Okay, so this was all about the types of fluid and the basics of fluid mechanics here. Now from the next video we are going to talk about the fluid statics, which we have talked about in the previous video also. Now guys, please keep practicing of the numericals of the fluid mechanics, because it has the really value for the numericals. And if you also want to that numerical video also, that we do a numerical video also for you people, then please comment in the comment box for that. And if you like the video, give it a thumbs up, and if you are new to our channel, don't forget to subscribe and hit the bell icon for more videos. You can also follow us on Instagram. The link is in the description. Our Instagram page is so much informative and valuable for you people, for civil engineers. So see you in the next video guys. Keep learning, keep supporting. Bye bye.